Hello, we are Project 19116, Rover for Exploring the Lunar South Pole.
Our team name is Mr. Ice, and my name is Lindsay I am the team lead and the computer and software subsystems lead.
I'm Trayton Moore, and I'm the structures and thermal lead.
I'm Madeline Ferguson, I'm the systems and instruments lead.
I'm Derek Bischoff, and I'm our power systems lead.
I'm Benjamin Champion, and I'm the GNC lead.
I'm Eli Seltzer, and I'm the mobility lead.
The problem our team was given was to investigate a permanently shadowed region and transmit this data back to Earth. Various different instruments were used on board this rover and a specially designed mobility system. The mass is 11.64 kilograms and the volume is roughly the size of a shoebox. The mission length is about 8 hours. In the end, our rover will be able to survive in extremely cold temperatures, traverse successfully over the lunar surface, and gather multiple forms of data. We have performed a WEG finite element analysis and vibration modeling to assure our rover will withstand these conditions. For the mission requirements, the objective was given by the NASA Big Idea Challenge. It stated that we must design a concept for NASA to use in future missions to explore permanently shadowed regions of the lunar South Pole and determine chemical composition of the regolith. On the right, you can see the design our team came up with. It is a rover. There are labels there showing the rover head, the rover body where most of the instrumentation is stored, and the wheels to let our rover move we refer to as WEGs.
Here is a brief overview of our concept of operations. We will begin by taking a rocket to the moon. Once we have arrived on the moon, we will exit the lander and move into the PSR. Inside the PSR, we will begin gathering data. Once we have collected enough data, we will exit the PSR and transmit this data back to Earth. Now we are going to go into the key rover components, specifically the critical parts. The instruments included in our rover are a camera, spectrometer, 2 thermocouples, an IMU, and a star tracker. Our rover is powered by batteries and a computer. Adhesives are used to mount the electronics onto the rover body. A universal mounting hub, screws, and brackets are used to attach the WEGs onto the rover body. A linear actuator is used for our rover head. This is connected to the rover body via bolts and brackets. The body itself is welded together, and the lid or top is attached with screws to allow for easy access.
The WEGs will be made out of a strong aluminum alloy. The mass of each WEG will be just over 272 grams. The radius of each is 8.6 centimeters, and they are all comprised of 5 feet and 5 legs as shown in the picture to the right. The edges of the feet allow for better gripping than conventional wheels, and the larger surface area on the bottom of the feet provide greater traction on icy surfaces.
To insulate our rover, we've chosen Pyrogel XTE, an aerogel, of 10 millimeter thick sheets with a density of 0.2 grams per cubic centimeter and a thermal conductivity of 20 milliwatts per meter Kelvin. This material is also hydrophobic, so as to prevent any latent water from depositing on the instruments. Each instrument will have up to 3 layers of this insulation surrounding all of its sides, with Supreme 10 HTS, a space-grade adhesive, being used to maintain the shape. This insulation will prevent the heat loss rate from exceeding 10 watts.
The rover will be transported to the lunar South Pole via a Falcon 9 rocket. Once the lander arrives, a ramp, similar to that of an airplane emergency exit, will inflate. The head of the rover will extrude while this happens. The rover will descend down the ramp and then make its way toward a permanently shadowed region at 2 centimeters per second. The rover will be able to maneuver using differential steering. The onboard camera will take pictures to assist in determining the rover's next movements. Relays will be dropped to assist with communications since the lander may not always be within line of sight. When the rover is in the PSR, the spectrometer will be pointed toward an area of regolith. The spectrometer will then determine the composition of the local regolith. The results will then be sent back to the lander using the relays. At the end of the mission, we would ideally expect to have various images of the PSR we explore, as well as the chemical composition of the regolith. As the regolith in the PSR has never seen sunlight, we would hope to find frozen water within it.
So for the development project, all of us really like space and want to do a space-related project. So we chose to participate in the NASA Big Competition, which was about exploring lunar PSRs. And we thought that the best way to accomplish all of the goals detailed in the competition were to design a rover. However, we were all aerospace engineering majors, so we had very little experience in many of the required fields to build a rover. For example, none of us had any real experience in electrical work, computers, software, or GNC, so we needed a lot of extensive research to design the rover. And this research included self-learning with textbooks, consultation with different mentors about both space and rover design, and other such things. So the initial design was presented and we received constructive feedback and tweaked the design and did that a couple of other times to reach the final design that was submitted to the competition.
Unfortunately, our structures lead was unable to stay on through the second semester of this project due to his graduate student duties. This forced our team to reorganize and redistribute his roles among our remaining members. Additionally, in early January, we submitted our proposal to the NASA Big Idea competition in hopes of receiving some funding for our project. Unfortunately, we learned that we would not be receiving any funding from NASA, forcing us to begin redesigning our rover for a lower budget. Recently, however, the ongoing pandemic has once again forced us to change tactics, as it meant that we could no longer construct any physical hardware or meet in person. Therefore, we began prioritizing simulations and animations to demonstrate our rover design.
As stated earlier in this presentation, the mission objective is to design a concept for NASA to use in future missions to explore permanently shadowed regions of the lunar South Pole and determine the chemical composition of the regolith, and our team knows our rover meets these requirements. It is able to survive in temperatures as low as 40 Kelvin, utilizing different insulation methods such as nichrome wire and pyrogel. It is able to travel to the PSR from the lander after multiple WEG iterations to find the best design to travel. And it is able to gather different forms of data in these permanently shadowed regions using a spectrometer, camera, and thermocouples.
From being a part of this project, we've learned about the engineering process. For any project, but especially ours, many design iterations are needed before a prototype can be built. Along with each iteration came reports, proposals, or presentations, all of which taught us the procedure that comes with engineering design work. Additionally, we learned about the limitations for rovers and other vehicles in space applications with a focus on mass. Of course, any group setting promotes team building through each member's strengths and weaknesses, but we also witnessed a great deal of personal development since none of us had previously worked on a project like this or on the subsystems we selected. Thank you for listening to our presentation.